Here's a pretty common projectile motion problem where instead of knowing the landing height of the projectile, I know the final x coordinate of the projectile. So I'm going to go ahead and put my origin right there at the launch point. A couple things you probably want to do before you even start reading the question maybe is put in the velocity components. So I have v naught x is 60 cosine 40. And I have v naught y. Almost got it straight up, but not quite. V naught y is 60 sine 40. And we'll go ahead and get some approximate numbers on these things. So 60 sine 40 is 38.6. I'm just going to round everything to 3 sig figs as I go. 38.6 meters per second. So this projectile is moving up that fast. The x component, 60 cosine 40, is going to be a 46.0. meters per second. And then as it says here in part A, so I want to compute the impact height that labeled h in the diagram, but I gave a hint. The final x coordinate is what's known here, so it's best to start with the x analysis of the problem. So if I write down the x equation of motion, remember there's no acceleration term for the x part because there are no forces acting horizontally in projectile motion. I'm starting from the origin, so that's 0. And I have my final x coordinate is known at 75 meters. My initial x velocity is 46.0 meters per second. And t is the only unknown there. So I'm going to be able to get t immediately. 75 divided by 46. And I get 1.63 for that. So that'll be useful. And I'll put a box around it to make it easy to find. What I want is the impact height. So that's a vertical consideration. So let's look at the vertical equation of motion. This is really just plugging in that the acceleration is negative g into that first kinematics equation in our list of kinematics equations. The initial y is 0. A common mistake here is for students to use the entire initial velocity of 60, but it's just the y component. It's 38.6. So when t equals 1.63, I have my impact at a height of h. So 38.6 times 1.63. Half of g is 4.9, so minus 4.9 times 1.63 seconds, all squared. And we'll crunch these numbers real quick. And I get 49.9 for that. All right, so the projectile hits the building about 50 meters above the ground. All right, then we get into the next part, the impact speed. So there's some stuff we don't know here. We don't know if the projectile is still going up or if it's already on its way down. And that will become apparent when we start to look at the final velocity components. Let's look at the x part first. The x velocity never changes because there's no acceleration in the x direction. So the final x velocity is going to be 46.0 meters per second. The y velocity, it does change because there's an acceleration of negative g vertically. So I'll plug in my initial y velocity, 38.6 minus 9.8 times the flight time, 1.63 seconds. And I get a final y velocity of 22.6, and that's positive, and that means something. So I'm going to put a plus on it, plus 22.6 meters per second. That means the projectile is still on its way up. So its y velocity has slowed down a little bit compared to what it started at, but it's still on its way up. All right, then I want the impact speed. I could ask, in general, I could ask you for the impact velocity, and you'd have to include an angle, but this time I just did the speed. So let's look at the x velocity here. That's 46.0. The y velocity, that's 22.6. And those add vectorially. And I get a final velocity vector. I'm going to call its magnitude v. And then I just use the Pythagorean theorem, and I say v is 46 squared plus 22.6 squared, square rooted. And I don't even need to get the angle here because it wasn't asked for it. And I get 51.3 meters per second for the impact velocity. I suppose I should just get the angle since we're right here. Theta is the angle whose tangent is 22.6 over 46.0. And I plug that in. And I get 26.2 degrees above the horizontal. 26.2. So the projectile is still on its way up. The velocity vector is still pointing up at 26.2 degrees above the horizontal.